Okay, so let's see, let us do some examples. Let us sketch some power functions. Okay, so sketch the function. And of course, we're gonna mix it up with some transformation, because if it is a basic graph like x to the n, we already know how it looks. Okay, so sketch the function, and let's see what do we have here. So let's do a couple. Let us do f of x equals 7 minus x to the 4. And then let us do, see, part B. Let us do g of x equals 1/2 times x minus 2 to the fifth power. Okay, so let us sketch the graph of these functions, and then let us also write the end behavior. So find the end behavior. Okay, so first let us go ahead and sketch the graph of these functions. So you should realize, first of all, let us focus on the first one, that the first one is the result of doing some transformations, right? So to make it more clear, maybe we should rewrite this a little bit. We can write this as negative x to the 4 plus 7, okay? So what is this? Well, there are two transformations that we're doing to the basic function. The basic function here is x to the 4, but then what are we doing to it? We're multiplying x to the 4 by -1. What it does is it flips the graph, right? Whatever was positive is now becoming negative. And then we're doing plus 7. That means we're shifting the picture up 7 units. Everybody okay with this? Do you remember these transformations that I'm talking about? The negative in front of the x to the 4 flips the graph, and then the plus 7 shifted up 7 units. Okay, so let's do this in steps. So first, in fact, I'm gonna do the flipping in one shot. Okay, let us first sketch negative x to the 4. And what is this? This is just the picture of x to the 4 but flipped. So instead of opening up, it's gonna open down, and once again, it's gonna go through 0, 0. But then instead of 1, 1 would be 1, -1, and then -1, -1. So it's gonna look like this, more or less. Remember, it has a parabolic shape, okay? It's a little bit more flat towards the x and so on. Here we're just sketching, so that's fine. So that's negative x to the 4. And now what we're gonna do is we're gonna take this picture and we're going to shift it up 7 units, okay? So now we're gonna graph negative x to the 4 plus 7. Which means take this picture that we have here and shift it up 7 units. All right, so the vertex, which is at 0, 0, now is gonna be up at 7. I'm gonna put it here, okay? And then this point 1, -1 is gonna be at 1,6. Let's see, let's put 6 here. Again, I'm not doing this to scale, okay? Otherwise, it would take me a big piece of paper to do it. And now we graph, okay? So, and then we're gonna use the same shape to graph this. So every time that you graph a function, if an intercept shows up, you need to find it, okay? So here we have a y-intercept, which is 0,7. That's already there, so we don't have to worry about it. But notice that there are two intercepts that showed up in here. So we should find these intercepts, okay? So those are the x-intercepts. How do we find these x-intercepts? Can anybody tell me? How do we find the x-intercepts of a function? Good, we put y equal to 0, okay? So basically, we need to solve the equation 7 minus x to the 4 equals 0, okay? So for example, let us actually, to get practice, let us solve this equation completely, okay? And to solve this equation completely, I encourage you to try to factor this as much as you can, okay? For example, notice that 7, even though it doesn't look like a perfect square, you can think of it as a perfect square, okay? So you can write 7 as square root 7 squared, okay? That's a little trick that we can x squared squared. So now we see that we have a difference of squares. So this would be square root 7 plus x squared times square root 7 minus x squared. Okay, that's equal to 0. So now we get here two equations. The first one is x squared, so square root 7 plus x squared equals 0. And then the other equation is square root 7 minus x squared equals to 0. The first one will lead us to something interesting because we get x squared equals negative square root 7. And what sort of solutions do we have here? Can anybody tell me? What type of solutions are we going to get? Are we going to get real numbers or are we going to get complex numbers as a solution here for this first equation that I'm solving? We're going to get complex, right? Because here we're going to use the square root method. So what do? X squared equals negative square root 7. So x is going to be plus or minus the square root of negative square root 7. So as you know, this is going to be plus or minus the square root of square root 7 and then times I, right? So put an I outside. Remember, square root 7, that's a number. You leave it like that because that's the exact number, but for example, you do square root and then you do it again. So square root 7 is about 1.62657, blah, blah, blah. Keeps on going that way, okay? That's a number, nothing wrong with that. But notice that we don't care about those because those are imaginary numbers and we only see two intercepts in the picture. Of course, those two intercepts, they are coming from the other equation because those are the real solutions. So let's solve all those. So we get that then x is going to be plus or minus the square root of the square root of 7. Okay? So those are our two intercepts, plus or minus square root of square root of 7. So this one right here is a positive guy, the square root of the square root of 7, and this one right here is a negative guy. Okay? But for example, notice that this polynomial is of degree 4, and we found 4 zeros, okay? 4 solutions to the equation. The 2 reals and the 2 imaginary. It's important. We're going to be talking about zeros of polynomials later on. And then we see a theorem that says that every polynomial has as many zeros as its degree. So we see degree 4, we're expecting 4 zeros. However, this is counting complex zeros. And in this case, we can see that among these 4, only 2 are real. The other 2 are imaginary numbers. Okay? Again, more on this would be later on when we talk about zeros. All right, questions on this picture. This right here is the picture of our function with all the necessary data. Okay? Questions on this one? All right, good. By the way, there is another way of writing the square root of 7. You can also write that as the fourth root of 7. Okay, so this can also be written as the fourth root of 7. And then this one would be minus the fourth root of 7. Oops, 4 goes outside. Okay, and an easy way to see that is, well, the square root of the square root of 7, you can write this as 7 to the 1/2. That's the first square root. Remember, when you have a fraction as an exponent, that's just a radical, and then to the 1/2 again, because of the second square root that we have. Okay? And now, as you know, the exponent of an exponent, you multiply. So this is 7 to the 1/4, which then gives you the 4 root of 7. Okay? So that's another way of seeing why, this is a way of seeing why that's the 4 root of 7. Okay. Anyways, questions on that one, on part A. Are there any questions here? All right, good. Let's see. Who can tell me the end behavior? Remember, by end behavior, what we mean is that you need to fill in this right here. So let's see, end behavior. And behavior. So as x approaches positive infinity, you need to tell me what happens to the function f. As x approaches negative infinity, you need to tell me what happens to the function f. So let's see, what's the end behavior of this function? When x approaches positive infinity, what can we say about f? Remember, f is the same thing as y, okay? F of x equals y. So what can we say about f of x? Negative infinity, very good. And what happens as x approaches negative infinity? What's the behavior to the left when x approaches negative infinity? It's also negative infinity. Very good. So this function begins down at negative infinity and finishes down at negative infinity. By that I mean when you're graphing from left to right, you're coming from below, and then you finish also towards negative infinity. All right? It's going to be important later on when we look at polynomials. Okay, so let us take a look at B. Can anybody tell me what transformations are we doing? So the basic function is x to the 5, right? Because we have degree 5, the fifth power. Now, how many transformations are we doing and what are they? Let's see, who can tell me how many transformations are we doing to the function g? We are in part B now. This way we are reviewing this transformation business. How many transformations are we doing? Okay, good. There are two transformations. What are they? Who can tell me? What are these transformations? So we're shifting to the right. How many units? We're shifting to the right 2 units. Good. And what else is going on? Okay, Sarah. So we are not flipping. So remember, the flipping means is when you multiply by a negative. But now we are not multiplying by anything negative, right? So this is a vertical compression. So we are compressing the graph vertically by a factor of 2. That's what multiplying by a half means. In other words, we are making our y values smaller. We are cutting those y values by a half. Okay? If the original picture had a y value of 4, for a given x, now our picture will have a value of 2 for that same x, and so on. Okay? That's what it means to compress the picture. It's going to get closer to the x-axis. All right, so remember, the flipping is when you multiply by a negative number. If you multiply by a -1, that's what flips the graph, okay? All right, so I don't feel like I have much space here, so let me scroll down here and do it. So we have g of x, it was 1/2 times x minus 2 to the 5th power. Okay, so again, we're gonna begin with the basic graph. Let's see, we're gonna do this in several steps. So let's begin with the basic graph, which is x to the 5th. Okay, so we need to know how this looks like, and this is where our knowledge comes from what we just discussed. How do powers functions look like? Well, x to the 5th, it has, this sort of shape, right? So it goes to 0, 0, 1, 1, and then -1, comma -1. All right. So now we're going to start moving this function around. Let's see, I always prefer to do all transformations that I can before I start moving my picture up and down or left and right, okay? So here, if you want, you could go to the right first and then do the vertical compression, but I prefer to first do the vertical compression and then I start moving around, okay? Because doing transformation, once you leave the original position of the picture, could create confusion sometimes. So, but again, up to you. So what I'm saying is, the first thing that I'm gonna do is, I'm gonna first do the compression. In other words, I'm going to first do 1/2 times x to the 5, okay? So what's happening from step 1 to step 2 is I'm multiplying by 1/2, And what that means is, in terms of the graph, is that we're doing a vertical compression. So vertical compression. Okay, in terms of the picture, all it means is the following. You give the shape, okay, it's the same sort of shape. It's just that these points, it's always good to have some basic points to move around. What we're going to do is we're going to reduce the y value by a half. Okay, so for example, 0, 0 stays there. All right, now the 0.11, the x value stays at 1, but now the y value, instead of being 1, is going to be 1/2, because we need to multiply by a half. So the y value goes down here, and then here it will be -1/2. So, it got closer to the x-axis. We took the picture and we did a compression. We vertically compress it. Okay? And now we're going to take this picture and we're going to move it to the right 2 units. So that's my last transformation, which is the actual function that we are interested in, which is x minus 2 to the 5th. So what's happening from step 2 to step 3 is that we are going right 2 units. So this time the y values are kept the way they are, and what we do is we add 2 to the x values, or the points that we see. So let's first move the points and then we graph. So the point that was at 0, 0 now is going to be at 2, 0. So let's say this is 1, this is 2. So that point is going to go here. Then -1, -1/2. Now that's going to go to 1, -1/2. So that point is going to go here. And then the other one is going to go to 3, 1/2. Again, we're just moving the graph 2 units to the right. And now we sketch. So again, same sort of picture. It's just that now it was moved to the right 2 units. Okay? And by showing these points, then it's clear that that's a function that we're talking about. If you want, you can show more fancy points. Like, for example, when x is equal to 4, let's see, who can tell me what is this y value that we have up here? When x is 4, who can tell me what is this? What is this point? 4, what would that be? What are the coordinates of that point? Anybody? What's the y value of this point? 16. Very good. That's the point 4, 16. And as I mentioned, remember, you should always, whenever possible, show the index. But if it's too big, then you're not going to draw that. What's the y-intercept here? The x-intercept, we can say, is 2. But at least let's write it down. What's the y-intercept for this function? Who can tell me what's the y-intercept? How do you find the y-intercept of a function? What do you do to find the y-intercept of a function? You make x equal to 0. Good. So can you guys tell me what it is? What's the y-intercept? -16. Very good. Be the point 0, -16. Okay. Now we have a complete picture of our function. I didn't draw the y-intercept because then I have to go too far down and so on. So I'm just making a note here next to the graph, so whoever is interested, they can see it there. Questions on how we produce this graph? And notice how we began with the knowledge of the basic function x to the 5th, and then we just did the corresponding transformation. Any questions? Okay, good. Let's see. M behavior. What's the M behavior here? Let's write it down. M behavior. So, and remember, this end behavior always means the same thing. When x approaches positive infinity and when x approaches negative infinity, what we say about the function? Let's see. What can we say about the function g when x approaches positive infinity? So when x approaches positive infinity, what do we say about g? So it goes to positive infinity as well. So like Maria is pointing out, as x increases, the y increases. All right. How about x approaching negative infinity? What can we say about g? It goes to negative infinity. Very good. Very good. Okay. So questions about graphing power functions and meaning their end behavior. Do you understand how to do this? Okay. All right. Perfect. Now, why is it that we care? I mean, after all, we're interested in polynomials in general. Why is it that we care about power functions in general? Well, because here is a very interesting theorem. Actually, when you want to sketch the graph of a function, you want to know the behavior. Okay, you want to know how the function begins and how the function finishes. By that I mean the graph, like where to begin drawing and where to finish drawing your function. And for polynomials, the point is that the end behavior of a polynomial is the same as the end behavior of its leading term. Okay, so that's a theorem. Write it down. So theorem, and this is a statement about end behavior of polynomials. And behavior of polynomials. So the end behavior of a polynomial function, so of a polynomial, is given by its leading term. So it's the same as its leading term. It's the same as the end behavior of its leading term. So in other words, what I'm saying here really is, i.e., that if you have a polynomial f of x equals an x to the n plus an minus 1, x to n minus 1, and so on, all the way up to a0, well, this polynomial will really be approximately the same as the function an times x to the n. And of course, when I say approximately the same, by this I mean when absolute value of x is large. In other words, when x approaches to either positive or negative infinity, your polynomial will look more and more like its leading term. Okay? In other words, this guy right here is the one that tells you what is going on with the behavior of the function for big values of x in the positive direction or in the negative direction towards negative infinity. Okay? So at least you know where to begin and where to finish. So example, find the end behavior of, and then let's see, let's put f of x equals negative 3 times x to the 9 plus 3000, x to the 5th minus x squared plus x plus 10 to the 20 to the 20. I'm just writing something, whatever, something crazy here. But this is a polynomial. Nobody can stop me from writing something. This is a polynomial. Okay? Notice that the last is just a big number, but it's a number. So that's okay. That's a polynomial. Now, we would like to know what's the end behavior of this polynomial. Now, according to the theorem, what is it that we should be looking at? What term in here determines how this function looks at infinity? Anybody? What term? Okay, so x to the 5th. Is x to the 5th the leading term? Remember, what does the theorem says? What term is the one that determines the end behavior of the function? Is the leading term. What's the leading term for this polynomial? The leading term is negative 3 times x to the 9. Very good. So this guy right here is the one that determines everything. Okay? So the end behavior of f is the same as y equals negative 3x to the 9. So in other words, you can just ignore the other guys. And I put very big numbers over there and so on, just to let you know, hey, it doesn't matter. At infinity, those numbers means nothing. Okay? The leading term is the one that takes charge of what's happening with the function. All right, so we reduce the analysis of f to this power function. Now let us analyze this power function. So when x approaches positive infinity, what can we say about the power function? And therefore, what can we say about f? And when x approaches negative infinity, what can we say about the power function? And therefore, what can we say about f? Let's see, when x approaches positive infinity, what can we say about the power function? My advice to you is do a quick sketch of how the power function looks like. X to the 9 will look like a cubic, but because of the negative, remember, you have to flip it, right? So this power function would have this sort of shape. Yes, this will be more or less the shape of the power function y equals negative 3x to the 9. Everybody okay with this? All right, and now with this little picture that we did here for the power function, we can actually see what was the end behavior. Let's see, because it's the same as our function. So when x approaches positive infinity, what can we say about f? We will go to negative infinity, right? And when x approaches negative infinity, what can we say about f? It goes to positive infinity. All right, questions? Any questions on this? All right, so how is this helpful? Well, this is helpful in the following sense. If you wanted to graph this crazy polynomial function that I wrote here, then what you know for sure is that whatever your picture is, it has to begin from up here, and then it needs to finish down here. Now, of course, still remains what happens here in the middle. Well, this is what we need to keep exploring and discussing. But at least we know that our function is going to begin from up here and it's going to finish down here. Do you understand this? That's what the end behavior tells us. How to begin and how to finish the picture. What happens in between? Well, we need to, analyze more. But at least we get a first step done. Questions? Okay, so that's how we're gonna be using this later on when we're sketching polynomials. Okay, we're gonna find the end behavior, and the end behavior is just the leading term. Okay, exactly. That's exactly what the theorem says. You read the statement. What is it saying? The end behavior of a polynomial is the same as its leading term. So the other guys, they don't matter. The lower degree terms, they do not play any role for the end behavior. They, of course, are important for the behavior of the function when x is small. But when x is big, the leading term is the one that tells you what's happening. Okay? All right, so I'm going to move on from this idea. Anybody needs any clarification? Okay, good. So now that we know this, then let's see what else. We would like now to see if we can try to sketch a graph of polynomials. Okay. So what I'm gonna do is I'm going to give you. We already know how to figure out the end behavior of a polynomial. Okay. So let me give you some information about the graph of a polynomial. Like some of the things that I will tell you, the reason why they're true, you need to wait until you learn calculus to understand this. Okay. But here is something important about the graph of a polynomial function. So I'm gonna label it as fact. Okay, so fact. The graph of a polynomial function is continuous and smooth. All right. So the graph of a polynomial the graph of a polynomial is continuous and smooth. Now, what do I mean by this? Okay, so I'm going to give you, again, these are notions that you're going to study in Calculus 1, but we need them now. We want to sketch the picture. So let me explain what I mean by continuous, at least the intuition behind that. So continuous basically means that you can sketch the graph without lifting your pencil. Okay, in other words, no gaps, no holes, nothing weird happening in the graph. So you can draw it without lifting your pencil. That's what we mean by the word continuous, roughly. Okay, there is a formal definition, but that requires calculus. So it means that it can be drawn without lifting the pencil. And of course, take pencil here in quotation mark, if you will, because like right now I'm using a digital pen, or you may be using a pen or something, but you know what I mean when I say pencil. All right, so can be drawn without lifting the pencil. That's what we mean by continuous. In particular, no holes, i.e., no holes or gaps in the graph. Okay. So for example, you're not gonna see something like this. This is not the graph of a polynomial function, or this and then this. This is not a graph of a polynomial function. Uh, this is not a graph of a polynomial function, because there are gaps here. You cannot draw this without lifting your pencil. Even though you could argue you don't have to lift the pencil for this, the first one, if you go around the circle, but that's not what we mean. Okay. All right, so that's the first thing. So the graph of polynomial function is a nice graph. It has to be continuous, but also it has to be smooth. What does smooth mean? Smooth means that when you're going to do a turn, you need to do it nicely. You cannot have sharp turns or corners on the graph. So that's what the word smooth means, roughly. Okay, this is the rough idea. So in calculus, you're gonna learn what it is. It actually means a smooth that is differentiable everywhere. Like at every point, you have derivative. You can make sense of tangent lines. But again, that would be a calculus 1 idea later on. For now, is no sharp turns. This is the intuition. No sharp turns or corners on the graph. Okay, so for example, you're drawing a picture, and then if all of a sudden you do something like this, well, this guy right here is not good. Okay, but if you're doing this and then you decide to go down like that, this guy right here is not good. Even though this picture is continuous, it's not smooth because we did a sharp turn there, making a corner point to show up. Okay, this one could be fixed nicely because you can do smooth turns like that. Okay, it means you're gonna turn, you need to do it nicely. That's basically what smooth means. Okay, nothing wrong. For example, absolute value, that's not a polynomial. Why? Because we have this corner point right here. Okay. All right. So that's the idea of continuous and smooth, and the functions that we are trying to study, the graph looks like this. Okay. So when we're graphing, we're gonna be dealing with smooth and continuous graphs. Okay. All right, so I'm gonna give you now some definitions to be able to understand graph. So there are some important points that you should have read about, which are what we call the turning points of the graph of a function. Okay, so a turning point is basically a point on the graph on which the function changes monotony. It goes from increasing to decreasing or from decreasing to increasing. So, for example, this picture, it has two turning points. It has one here, somewhere there, and another one here. Why? Because it went from increasing to decreasing around this point. That's a turning point, and here it went from decreasing to increasing. Okay, so that's what we mean by turning points. So I'll leave this here, and I'll call this turning point, and this guy right here is going to be another turning point. So let me write it down. So definition, and point on the graph so the point on the graph of y equal f of x is called a turning point. It's called a turning point if the graph of f changes monotony around the point. Okay, so if the function, monotony is a fancy word for increasing and decreasing. Okay, if the function changes monotony around the point. Around the point. So in other words, changes from increasing to decreasing or vice versa. From increasing to decreasing or the other way around. So that's what a turning point is. Now there was a very important theorem that you saw in the in your reading and in the videos that you watched and so on, which has to do with polynomial functions and the number of turning points that it could have. So can anybody tell me what is this? So if you have a polynomial function, let's say of degree 20, can you tell me how many turning points was the maximum number of turning points that it could have? Anybody? If you have a polynomial of degree 20, what's the maximum number of turning points that it could have? Very good, sir. 19. Very good. So for example, that picture that I did here, the picture that you're seeing on the screen, can you tell me what's the, imagine that this is a polynomial. Could you tell me what would be the degree of this polynomial, or the smallest possible degree that this polynomial could have? Very good, 3. Why? Because we have 2 turning points. In other words, the theorem says that a polynomial of degree n has at most n minus 1 turning points. Okay? So if you see that a polynomial has 2 turning points, then the degree has to be 3 or bigger. Okay? So we already know that the picture that we have on top belongs to a polynomial of degree 3 or maybe larger, because we don't know what's happening down the line, okay? But it's at least 3 for sure. Good. So theorem. Again, to justify this theorem, well, you need calculus, okay? So the graph of a polynomial, the graph of a polynomial function of degree n has, and this is important, at most, okay? So that means no more than, okay? At most n minus 1 turning points. It could have less, but no more. For example, there are polynomial functions with no turning points. It may have 0 turning points, okay? At most n minus 1 turning points. In other words, this word at most really translates into less than or equal to, okay? And like I said, the proof for this, it needs calculus. So it needs calculus. In calculus, you're gonna learn some ideas that will allow you to justify something like this pretty easily. All right, so the graph of polynomial function of degree n has at most n minus 1 turning points. This is important. And I want you to keep in mind that there could be no turning point. For example, think about x cubed, right? So if you think about y equals x cubed, the graph is like this. It has no turning point. It's always increasing, but the degree is 3, okay? So it doesn't mean that you will always have n minus 1 turning points. What the theorem says is you have at most no more than n minus 1 turning points, okay? You could have less or even none, like any power function with odd degree, 3 or 7 or 21, whatever, is not going to have any turning point, okay? All right. Anyways, questions on this theorem? Does everybody remember reading this theorem and doing problems on this? There were video assignments and so on this theorem. Okay, so this is important because this tells you what to expect when you look at a picture. When you look at a formula, this is telling you what to expect. How many turning points can you do maximum? All right, so now we have this. Another idea that we need to be able to sketch is the notion of the zero of a polynomial. Okay, and once we understand this, then we can start creating some pictures. All right, so let me write that down. So definition of zeros, and then the whole business of finding zeros of polynomials or roots. This is actually very hard in general, and we're gonna spend a whole section just trying to figure out how we can find zeros of polynomials. Okay, but once you know the zeros of a polynomial, then the point is that then it's very easy to analyze it. Okay, so to graph a polynomial, all you need is leading term, so you know the end behavior, of course, the degree, and the zeros. Once you know this information, that's it. You can draw your picture. Okay. All right. So let me write this down. So definition: what's a zero? A zero is just what we call the root of a function. It's a value of x that makes a function equal to zero. Okay. So suppose that we have a function. So let y equal f of x, and this is true for any function, not just for polynomials. Be a function, and let x equals c be a real number. On the domain of f, of course, it has to be something I'm plugging into the function. On the domain of f, then if f of c equals 0, in other words, if when you plug in this number you get 0, then x equals c is called a 0 or root of f. A 0 or root, we also use sometimes the word of f. 0 or root of f. Okay. So in the case of polynomials, of course, we have this idea of 0 because polynomials are functions, but also there is this other notion of multiplicity. So a root, a function may have, a polynomial function may have a root with a certain multiplicity. So what is this? What is this multiplicity business? Well, this has to do with the number of factors that the polynomial has when you factor it completely with a given 0. Okay. So let me say like this. So it's number one, number two. So if f is a polynomial function, if f is a polynomial function with x equals c a root, and x minus c appears exactly k times in the complete factorization of f. Remember, every polynomial, you're going to learn the fundamental theorem of algebra will tell us that it can always be factored, okay? And in fact, you can always factor it as a product of linear factors. This is using complex numbers also, okay? So that's the catch. So if f is a polynomial function with x equals c a root, and x minus c appears exactly k times in the complete factorization, of f. If this happens, then uh, x equals c is said to be a root of 0 of multiplicity k. All right. So in other words, so what I mean is if when you factor the polynomial f, let's say that you can factor it as x minus c, and this will be a theorem that you're going to see, that if c is a 0, then x minus c is a factor, okay? And this follows from division. We're going to study this when we start looking at zeros. So that means that you can factor f of x as x minus c to the k power times some other function, okay? But the point is that c is no longer a root in G. In other words, G doesn't have x minus c as a factor anymore. So this where G of c is different than 0. That's what it means to say that x minus c appears exactly k times. You factor it out as many times as you can, and then whatever is left over, c is no longer 0. Okay? In that case, this number that shows up here, this k, is called the multiplicity of the 0 c. Okay? And this has an effect on the graph of the function, as you probably have read already. So let's see, let me write down an example. So I'm gonna give you a polynomial, and then we're gonna find the zeros and the multiplicities of this polynomial. So find the zeros and multiplicity, and their multiplicity. Okay, and the multiplicity. And let's see, the polynomial, the first one that we're gonna take a look at will be g of x equals 1 over 4x times 2x minus 3 cubed times x plus 4 squared. Again, we cannot do something too interesting at this point because we don't know how to find zeros in general, okay? Of course, when the polynomial is given to you like this in a factor form, it's straightforward how to find the zeros. But when it's given to you in the expanded form, that's when the job begins, okay? It gets pretty hard at that point. But we're gonna be studying that little by little. All right, so let's see, just to understand this idea of multiplicity. Let us list the zeros of this polynomial, and then we're gonna write their multiplicities, okay? So zeros in this column, and then next to it, we're gonna write the multiplicity of each of the zero, okay? So let's see, can anybody tell me what are the zeros of this polynomial? Remember, a zero is basically is the same thing as x-intercept as well. So it's whatever makes the function equal to 0. So what is it that we need to do to figure out the zeros of this polynomial? Anybody? What do we need to do to find the zeros of this polynomial? So we set the polynomial equal to 0, which in this case means setting each factor equal to 0. Very good, Giovanni, right? By using the zero product rule. So let's see, when you set the polynomial equal to 0, so we want to solve g of x equals 0, it follows that we will need to solve these three equations, right? 1 over 4x equals 0, or 2x minus 3 cubed equals 0, or x plus 4 squared equals 0. And then it follows that we got x equals 0, or x equals 3 half, right? Or x equals negative 4. What we have here are zeros. So 0, 3 half, and negative 4. Those are the three zeros of this polynomial. Now let us figure out the multiplicities. So let's see, what's the multiplicity of 0? So again, for that, very good. You have to look at the factorization and see what's the, notice that this is the complete factorization. There is nothing more we can factor here. So the term that gives you 0 is the x, and it has power 1. So that means multiplicity is 1. Let's see, the term that gives you 3 half, what is it? What's the factor that gives you 3 half as a 0? That's the factor 2x minus 3. What's the multiplicity? What's the power that that factor has? It's 3, so that means we have multiplicity 3. Very good. And now the term that gives you negative 4 as a 0, the factor that gives you negative 4 as a 0, is x plus 4. What's the power that it has? 2. So that's the multiplicity of that 0. Good. So questions on figuring out the multiplicity of a 0 once you have the polynomial factored out. Notice that this would be very hard if it was not given to you in a factor form. But if you have already your function factored out, understand how to write down the multiplicities. Are you okay with this idea of multiplicity? If you don't understand something, let me know, and then I'll explain again. So Ram says, is the multiplicity of each term provided that you have the complete factorization. You have to be very careful, okay? You have to make sure that the polynomial is completely factored. Once you factor it completely, the multiplicity of a zero is the power that the corresponding factor has, okay? And remember, you need to know what multiplicity corresponds to what zero. For example, 1 corresponds to the 0, 0. The 3 that we see there as a power corresponds to 3 half, and the 2 that we see as a power corresponds to -4. Are we good with this? All right, perfect. Okay, so now that we know what multiplicity is, the question is, what is this good for? I mean, why do we care about multiplicity? Can anybody tell me? Do you remember reading about this? What does the multiplicity tells you about the function? So we know that this is a zero, meaning we know that at this point, for example, imagine that you wanted to graph this function. Yes? In fact, let me go ahead and let's say that we wanted to graph this function, and I wanna, right here, you're gonna see how is it that we're gonna be sketching functions, okay? So let's say that we wanted to graph this function. What is it that we should do? So first we know we know the zeros, right? So the zeros are 0. So let's put it here. So if you wanted to sketch a graph of this function, we know that it has to go through those 3 points. So let's say here is 0, then say that this is 1, then this is 2, so 3 half is here. Okay, here we have 3 half, then we have -4. 1, 2, 3, 4 here. So we have to go through these 3 points. Okay. Then of course we also know the end behavior. So to graph this, we should take a look at the end behavior. Let's see what's the end behavior of this function. Let's see, we're gonna graph in red. So let me put these points in red. What's the end behavior of this function? Can anybody tell me? What's the degree of this polynomial? Because after all, we need to know what's the end behavior. What's the degree of this polynomial? Okay, so we have 2 candidates. We have 3. We have 5. Anybody else? What's the degree of this polynomial? So remember, to know the degree, you need to have it in standard form, meaning you need to have it expanded, and the degree will be the highest power. So what do you think is the highest power here? All right, the 3 is just this one right here, yes? But what happens when you multiply these 2 guys? What power are you gonna get? You're gonna get 5, yes? But what happens when you multiply this little guy with those other? What will be the power? Oh, it will be 6, right? So you have to be careful. So the power is 6, okay? So this is gonna be, if you were to multiply this would be something times x to the 6 plus lower guys. Now let's figure out that something, because that something is important also. What's the leading coefficient? Remember, we are after the leading term here. So I already know the literal part. Now we need to know the leading coefficient. What will be the leading term? Can anybody see it? You don't have to multiply everything, but you should understand what happens here. For example, for this term right here, when you do that cubic, what will be the leading term of that little factor? That would be 2 cubed times x cubed, right? So that would be 8x cubed. Everybody okay with this so far? For that little parenthesis, you will have ax cubed plus some other little stuff. So when you do the cubic, you're gonna have, you will have 2x to the cube, which is ax cubed. What I'm saying is 2x minus 3 cubic. When you expand this is gonna be a cube plus ax cubed plus all stuff. Okay, the highest term will be this one. Okay, now the parenthesis with the square, the highest term here is gonna be x squared plus all the stuff. Yes, so when you multiply so far, you're gonna have 8 times x to the 5th when you multiply these 2 guys. And then when you distribute this one, you're going to have the x to the 6, as we know, but then would be a quarter times a. So that's going to give you 2. All right? So, you don't have to multiply the whole thing, but when you analyze, then you will see that the leading term of this polynomial is 2 times x to the 6. Can everybody see this? Or do I need to explain this again? And remember, this is important if we want to know the end behavior. You need to be aware of the degree and the leading coefficient. So, okay, again. Okay, the x to the 6, is that okay with everybody? The power x to the 6, that's okay. All right, so let us figure out now this one, okay? The coefficient. Again, we have 1 over 4 times x times 2x. I'm writing it here to have myself more space. Okay, so imagine that you were multiplying this. Okay, and that's really what we want to multiply all of this and see what's the biggest guy. Now, we're not going to actually do it. We're just going to look at what we need. So from this parenthesis, the highest term that will pop up would be 8x cubed. And then all the stuff. That's what's going to happen in this parenthesis. Are we following so far? All right. Now, in the other parenthesis, when you multiply, what you're going to have? You're going to have x squared. In fact, this one is easy, so let's do it completely. You're going to have x squared plus ax plus 16. Right? That's what you're going to get for the second parenthesis. But again, the other stuff is not important. What's important is x squared. And then remember that we have a 1 over 4x. So what will happen when we multiply? When we multiply these two parentheses using our distributive property, the biggest guy will be a times x to the 5th plus some other stuff. Everybody okay? Are we following this so far? All right. And then we have this 1 over 4x. When you finally multiply this guy, what is it that we're going to get? We're going to have 2x to the 6 plus lower degree terms. Because 1 over 4 times 8 is 2. Are we good with this? All right, perfect. So so the point is that if you have the polynomial given to you in factor form, you need to be able to recognize what the leading term is. Okay, so we need to do this kind of analysis and be careful, because if you end up with a negative leading coefficient, that's gonna change the behavior and so on. Anyways, this is 2x to the 6, so that means that the leading term here is 2x to the 6. Okay, so what's the end behavior of this function? Because the power is even and the coefficient is positive, that means we're going to begin up here and we're going to finish up here. Yes, so we know that whatever we do, we come from up here and we finish we come from positive infinity and we finish at positive infinity on the y-axis. So as x increases, y increases, and as x decreases, y also increases. So we come from positive infinity and we finish at positive infinity. Are we okay with this so far? All right. So now that we know this, then that means that we're going to come from positive infinity, right? So we're coming from up here. And the first time we're going to hit at some point, we're going to hit, and again, we're sketching here. We don't know if we're doing this kind of stuff. At least we don't know that yet. But let us just look at the simple stuff. So we come from positive infinity and then we're going to hit -4. Now we have two choices at -4. We either cross it or we bump off. In other words, at -4, we could do this. We could go through it like that, okay? Or we could do this, okay? We could bounce up at -4. So the question is, how do we know what do we do? Do we go through -4 or do we bounce at -4? Okay, and the answer to that lies in the multiplicity. Okay, so in some of the readings that you should have done, then it tells you that the multiplicity gives you exactly this information. And even multiplicity means that at that 0, the graph of the function is going to bounce up the x-axis. So you're gonna touch the point only. You're not gonna cross it. Okay. So if your function was positive to the left, it remains positive to the right. If it was negative to the left, it remains negative to the right. So even multiplicity means you touch the x-axis. Odd multiplicity means you cross the x-axis. So this right here means that we're gonna touch the x-axis, okay? And this guys means that we're gonna cross the x-axis, okay? So by doing this, I know that when we're graphing this, come from positive infinity, then we hit -4, we're gonna bounce back up, okay? We're just gonna touch it. We're not gonna go below the x-axis here, all right? So we're gonna keep on going. We're gonna keep on doing our business. At some point, we need to come back because we need to hit 0. Okay, so somewhere we need to hit 0, and now we need to cross 0 because notice that the multiplicity is 1. Now the question is, how do we cross it? Because for example, when you have a point, you could cross the point this way, okay, like a line, but you could also cross in a cubic fashion, like that, or you could, there are many ways that you could cross the point. How do you do it? Well, the multiplicity tells you. If you have multiplicity 1, you're gonna cross like a line. If you have multiplicity 3, you're gonna cross like y cubed, like x cubed. If you have multiplicity 5, you cross like x to the 5, and so on. Okay, so in this case, we're gonna cross like a line. So just cross 0. So if you zoom in, you're gonna see something straight. At some point here, we need to come back up, okay? And then when we come back up, we need to cross 3/2, and we need to do it with multiplicity 3. So meaning it has to look like a cube, okay? So let me draw something that looks cubic-like here. So that means when you zoom in around that point, you should be seeing the graph of a cube, okay? Let's fix it like that. All right, something like this, okay? And I'm saying something like this because there are still a lot of unknowns here. Like for example, how high do we go here? How low do we go here? Well, you won't know that until you learn calculus. In calculus, you're gonna learn exactly what those points are. Here, what you could do is draw a sketch, a bunch of values, okay? Do a table of values, and you could more or less estimate what these points are. But in general, this is the shape of the function. Also, let's take a look at it. How many turning points do we have here in this picture? We have 1, 2, 3 turning points. Well, the degree was 6, so you could have up to 5 turning points. So, maybe there was a turning point somewhere up here that would add to and complete it to 5 turning points, but that we don't know, okay? Until you learn calculus, you're going to be able to know precisely how many. But this would be a reasonable sketch of this function. Did you understand how we use the information of n behavior, zeros, and multiplicity to produce this picture? Because this is basically what you're going to be doing. Once you have a polynomial, you're going to be trying to figure out the zeros, the multiplicity, so that then you can sketch the graph. And this is basically what it boils down to. Okay, I lost the chat. Okay, yes. Okay, good. So you can go to Desmos it's an online graphing calculator, and it's free, and it's actually pretty cool. For example, you can play with all the stuff that I was saying before. Here is x squared. Okay, then here is y equal x to the 4, and here is y equals x to the 6, for example. You see red, blue, and green, and as you can see, between -1 and 1, we have the relationship that we're talking about. But as you pass 1, 1, or x bigger than 1 or x less than -1, then the highest exponent, that one takes over. But if we zoom out, for example, notice how now from far away, the green and the blue, they already seem the same. And if you start zooming out, eventually you will see that they become next to each other. Okay. All right. But basically, what I wanted to show you was the other function. So let's do that one. The other function was y equals 1/4 times x, and then what was it? 3, no, it was 2x minus 3, and then the power was, how's the power here? What was the power? Was it 3 or I forgot? So it was 12 minus 3 to the cube, and then the other one is x plus 4 squared. Okay. All right. So it looks like we need to zoom out. Let's see. So at least here, okay, let's look at pieces of the graph. So first of all, here we see the 3 zeros, okay? Notice that here in this part, we see the behavior that we were discussing, right? So at 1.5, which is 3.3 half, we see that it's going through in a cubic fashion, okay? If we zoom in around 0, it's very steep, but hopefully you can see, I mean, it's very hard to see, but you can see that it's going through 0. It looks like a straight line, really, okay? And wow, and then here at -4, remember the multiplicity was 2, and then when we get very close to it, you can see how it looks like a parabola, okay? When we are close to -4. It's kind of hard to get an overall picture because it looks like it shoots very high, the function. Of course, because the degree is tall, right? So let's see how high it goes here before it goes down. Oh, it's shooting very high. Where is it? Well, anyways, oh, here it is. So the point where this turning point happens is more or less here at 730.228. Okay. Again, you're gonna be able to figure this out precisely when you learn calculus. Okay. We know that at some point it's gonna turn around. Okay. So that's your function. So we cannot get a whole picture because this is too high, so we won't be able to get it on the screen unless I maybe do this. Let's see the x. I really just want it between -5 and let's say 3, and then the y, let's say between -50. Okay, there we get. We have there a good picture. We can see a good overall behavior of the function. Okay, so it comes from up from positive infinity, then we bounce back at -4. At some point we come back down. We go through 0 in a linear way. Remember, if you zoom in here at 0, you're gonna see that this will look like a straight line. Okay, if you zoom in at 0, and then at some point comes back up, and then we go to 3 half, but in a cubic fashion. Then we keep on going up. Okay, so it's somewhat close to what we had sketched. Anyways, this is a good little tool that you can use to your advantage. Okay, when you're graphing stuff, then you can use it to check, make sure that you did it correct. Okay, so I believe, let's see, let's put this here. The picture that we had was something like this. Hasn't synced. Okay, yeah. I mean, of course, this is up to scale, but it's pretty close to what we were having.
Yeah, I just had a question on the 3.4 video thing that we had to do. It was one of the assignments. And I was just having a little bit of trouble with question number 7, which is basically writing an equation for the polynomial graph below. So I understand from today's lesson how to graph it, but how would I kind of struggled a little bit making the equation from the graph that was shown.
Okay, so that's 3.4.
Yes.
Video assignment 3.4. Yes. So let's see. Number 7. This one. Okay. So remember, as I mentioned, and the zeros really is the one that tells you everything, right? So let's see, how many zeros do we see here? I'm gonna do this one that I have on the screen. Probably yours, the numbers are different, okay? But I'm gonna do this one that are on the screen because it's the same idea. For example, here we see 1, 2, 3, 4 zeros. Yes? So the
Yeah.
zeros are -3, -2, 2, and 4. So each of those will give you a factor for the polynomial. Okay? So for example, this means that x plus 3 is a factor, x plus 2 is a factor, minus 2, and x plus 4, and x minus 4, sorry. Now we just have to figure out the multiplicity. So what power would that factor have? If you see here, notice that this is odd because we're crossing, odd because we're crossing, odd, and this one is even because we're touching, all right? Now, here we're crossing in a linear way. We're not doing any funny movement like the cubic. So this is multiplicity 1, multiplicity 1. This is also multiplicity 1. And this one, they usually tells you the lowest possible degree. So we're going to take this as multiplicity 2. Okay. So far, what that means is the following. These are the factors so far. X plus 3, because of the first zero. So x plus 3. Then the other factor, and that's multiplicity 1, so power 1. Then x plus 2, because of the second zero. Then we have x minus 2, because of the third zero, and they all have multiplicity 1. Now the last one would be x minus 4, because we're touching the multiplicity is 2, because again, we're looking for the lowest degree. So I'm going to put a power of 2, okay? So far, this one.
So it's power of 2 because it's even and it's only touching the x-axis?
Yeah, exactly. Okay. Yeah. For example, if you look at the video example that is in here, without me playing it, you can see here, this 0 and -2 is touching, right? And then telling you the multiplicity is 2, right? And this one here is crossing. I don't know if you can see it, but it's crossing like a cubic, so the multiplicity is 3. This here. But okay, let's come back here. Now we have this. However, this could have a leading coefficient, because so far here we have leading coefficient 1. I didn't put any numbers here. In general, there could be some number here multiplying this whole thing. Okay. So we have to figure out what this number is. And for that, you will need an extra point. And another point that's easy to see is this one, the y-intercept. Notice that the y-intercept here is 1. What that means is that when x is 0, y is equal to 1. Okay? So we're going to use that to figure out the number that goes in here. So for that, we need to plug in a little equation. So if I call this a, when x is equal to 0, y is 1. So let's see. I think we can do this out loud. When x is 0, what do we get here in the parentheses? We're going to have 16. Then here we have -2. That's going to be -32. And here we're going to have +2, so that's -64. So -64 times 3, that's -192. So we get y equals a times 192 when x is 0, but when x is 0, y should be 1. So that means a is going to be 1 over -992. So this should be a polynomial function. Okay. Let's see. Let's check it and then we talk about it. Yeah, there we go. So again, let me say this again. You look at the zeros, right? That's gonna give you the factors, and of course you need to adjust the multiplicity the way they should go, and you have to look at the picture and see how you're crossing. And after that, once you have this part right here figured out, then you need to figure out what number goes here. What's the leading term? Okay, what's the leading coefficient? And for that, well, because if you don't put that, then you're saying that the leading coefficient is 1. And notice it was not the case here. For that, you have to look for another point in the graph. Here we have 1, which is 0,1. We can see it in the picture. So that means when x is 0, y is 1. So you just call this guy, I don't know, call it a, plug in x equals 0, y equals 1, and then you solve for a. It turns out that here a was -1 over 192.
Again, why is it that you put it in a fraction as opposed to just -192?
Oh, no, because it's 1 over 192. It's -1 over 192. Because we had y was 1, So 1 equals negative 192 times a. So when you solve for it, you have to divide.
Okay, now I understand.
I'll have to write, but then if I write, then the screen is gone. Let's see. I wonder if I could do it here. So basically you have y equals 1, and then when you plug in x equals 0, on the left you will have a times, and then all of those parentheses, when you put x equals 0, you're going to get negative 192. Okay? And so that means that the a, which is the leading coefficient, would be negative 1 over 192.
Okay, awesome. Thank you so much, Professor.
Right? Yeah, no problem. Okay, good. Any other questions? So let's see, Maria, but for now we cannot tell from a graph a multiplicity larger than 3 if it is odd, right? Yes, so usually in these problems they will tell you find the least possible degree, okay? So, in this case here, I would say for the least possible degree, I would say multiplicity is 2. It could have been 4, or it could have been 6, the multiplicity here when x is 4. But we're always looking for the lowest degree, so we just pick it to be 2, okay? And also you have to look at the turning points. How many turning points do we have here? 1, 2, 3, 4 turning points. So the least degree that this polynomial could have is 5. That's another thing that you can do to check. So 1, 1, 1, and 2. So that's degree 5. So we're good. It could be higher, okay? But definitely no less. If somehow you had a couple more turning points up here, then you will have to bump it by 2. So instead of degree 2 here, multiplicity 2, I would say multiplicity 4. But the picture will have to tell you that. Okay? You just need to use everything that all the knowledge that you have right now for that.